Okay. Good. So in the past couple of lectures, we got stuck on equation 50 here in an alternative derivation of the plane parallel approximation. So it was during last lecture we realized that this last term here is not always zero. So that's why I couldn't prove it 2 lectures ago. This we realized by checking the textbook I got this from, which is the book by Frank Shu. And this is only zero when the phase function is forward-backward symmetric. And so during last lecture, Felipe pointed out that this means that the function is even. So this is basically what we said. So for forward-backward symmetry, we have this situation where phi of k prime is the same as phi in the opposite direction. And it also works reverting k prime. Okay, so basically this means that well, we made the sketch last time. We have a dust grain. This would be like the k direction, like this. Okay, so basically it means that if k is let me draw k prime. So this would be k prime. Okay, so basically it means that scattering from here to there is the same as scattering in the opposite direction and coming back along k again. Okay, forward backward scattering symmetry means that the phase function is even. Okay, and in this case the this integral, let's call it a, this integral d omega k phi of k prime, k prime, this is 0. Now to see this, we made an example component, but this is actually quite obvious because this can also be spelled like this. So we have in the integral in d theta from 0 to pi times the integral in phi. So this is the omega, right? So and sine theta, so that would be d omega times okay, so times k and phi, as we write it above. Okay, and k has got coordinates theta and phi in spherical coordinates. Okay, so I make a change of variables now. I say L is minus k, and then in this case we have the solid angle variables are minus theta d theta times the integral of minus d phi times sine of minus theta here times minus L times phi of minus L k prime. Now this one is even, so it's the same as the others, and we have finally that this is am I doing things right? Yes, I think so. And this goes from 2 pi to 0. Maybe I should put a subscript. So I'm just putting a nail here just to distinguish from the previous theta. So this means that theta L is minus theta, and that phi L is minus phi. So okay, and this one, no, this isn't 2 pi, this is only pi. Let me find the eraser here. Okay. And this goes from a 2 pi to 0. Please interrupt me if I'm doing something wrong. Okay, so this should be then, if I did not make any mistakes, this is then the integral from 0 to pi from d theta L from the integral of d phi L from 0 to 2 pi. Now this is sine theta L, but I've got a minus coming out here. And then there's this other minus here. So we have L phi L k prime. I think I made something wrong again. This isn't right. If I change the direction of k into minus k, this isn't true. If I put k into minus k, we have theta L is theta plus pi. This is this is pi minus theta. Can you help me out with this one maybe?
I think phi will remain same. Only theta will change the sign.
Let me see.
If I have to check.
So I'm drawing it here. So that would be a k. That would be theta and phi. That would be phi here. And now we have minus k going in the opposite direction. So theta is pi minus theta. And it's kind of hard to see in my drawing. What you're saying, Patrick, that phi would be the same? I don't think it would be the same. I think it should be.
No, it won't.
No. I think what's the symmetry here? It's
So this so it will be just opposite to this k prime. So that's
no. I mean, we're reverting. I'm changing variables from L to k and treating k prime fixed. So L is minus k. It's pointing in the opposite direction. So I think that it's okay that theta L would be pi minus theta. That one is okay, but phi then it's kind of hard to see from this perspective. I think that phi would be minus phi. Or maybe if we look at it from the top, look at it from the top. So this is x, y, z. So this is z coming up here, x and y. And so we have that's k. And this one here is L. Okay, so this is phi, and this other one would be phi L. No, that's incorrect. This is phi L. Okay, so I think this, I need to correct my equation here. It's phi plus pi. That is okay. That's
Yes.
horrible,
Yes.
but
Yes.
I'll get there eventually. This is phi plus pi. I think that's the correct. Okay, that makes more sense. So in this case, d theta L is okay. There's a minus here, but this one is plus. Actually, and now the direction of integrations. This goes from so if phi is 0, this is going to go from pi to 3 pi. And
yeah, now it's taking shape, I think. I
Yeah.
equal to minus I, then suppose that integration a equal to minus a, I think now.
that's
And then
what that is
yeah,
what I want to get to.
I think now it's taking shapes. I think it has taken shape. Because you
Let's
have used you have used this forward and backward scattering for the last time.
Yeah.
Again, yeah. So I think now it's, yeah, I think it's fine. I think.
But I'm not sure because
Okay, fine.
because this theta. I mean, let me just be completely certain about this, because theta L then goes from pi to, and when theta is, oh, that's all right. This goes from pi to 0. This is correct.
Yeah.
Yes, but it doesn't have a minus because it goes from pi to 0. There's no minus in there, right?
But the d theta, when I change it to d theta L, it's got a minus, no? Felipe?
D theta L.
Yeah, when I change, that's what I mean.
So this is pi.
Oh, right. Sorry, I didn't see it.
So I think this is a new variable. Okay, so indeed, when I with this minus, I can change the order of integration from pi to 0 to pi. So this is the same as the integral over d theta L. This minus here goes, this is not correct. Let me erase this equation then, because this is not true. Here, that, and that's not true either. Theta L minus theta L plus pi. And this goes from pi to oof. Well, well, okay, so we have a minus here, and this still goes there. Okay. Then we have that the sine of theta is the same as sine of pi minus theta, I think. This is the same as sine theta L. All right. Do we agree on this?
Yes,
Yes,
I see it.
so. Mhm. Okay, and so this is almost A, except that the limits of integration of phi are shifted by pi. So, okay, we remember that this is another function.
But maybe we can use that the period of sine of pi is 2 pi, so we can move the integration limits to pi. Then we can integrate from minus pi to pi.
Yes, but it's still not zero from 0 to 2 pi. Okay, so I think we are almost there, except that we have a problem with this part of the integral, which is the part in phi, which would be the integral over d phi from pi to 3 pi times L and phi. So now, why would this be equal to the same integral shifted by pi? There's something I'm not getting right. L is, I think this is correct, but okay, I don't want to lose the hour on this again. Sorry, I thought it was obvious this time, but I did it earlier today, but without going through the components, just looking at this again. It's not so clear when I go through the components. Maybe you guys can explain to me later on why this is the 0 in the general case. I think last time we proved this with the vertical component kz, right? We did that. So I'm trying to do it in the general way, but I'm losing too much time. So help me out with this one, guys. Please find a proof in a general way, and maybe we can discuss this over the forum in uCursos. But I'm stuck with this part because if this was from 0 to 2 pi, then we're set. It's the same as A, and then we have in the end that A is minus A, and so A is 0. Okay, that's where I'm want to get at. But we don't have that. We have that these integration limits are from pi to 3 pi, and so I think that Felipe, you're right. It probably goes in along the direction that we have an angle here that goes from 0 to 2 pi, so it should be the same to integrate from pi to 3 pi and from 0 to 2 pi. But all of a sudden, I'm not sure I can prove this. I mean, the argument should be periodic in phi. Wait. I mean, I know that this is true, that this is the same as, I mean, can you see any easy proof of why this, if we have, like, I'll put it another way. This is of any function of phi from pi to 3 pi is the same as that's what I want to prove. I think it's true, but
well, I think that well, I think we can prove we can say that if the function f has a period of pi, not 2 pi, if it has a pi period, then I think it's you can shift the integration limits, which I think is also true because of the drawing of the phi function, which has two lobes, meaning that the first lobe is the same as the second. So pi term is the same. So it has so you can say that the phi has a period of pi. And then you can say that.
yeah,
And if
normally we
the
have that if k is if k prime is parallel to z, okay, then we have that phi of k in the direction z, that would have symmetry in phi, is constant in phi, is what I mean to say, because of the drawing you're mentioning, Felipe. Okay, so because what Felipe is referring to is this: we have a bipolar structure like this for phi. Okay, this would be backwards, forwards, backwards symmetric phase function. So that would be the obstacle here, and phi is this variable, right? So it's symmetric in phi. Okay, so in this case, it's phi is obviously symmetric in this direction. Now here we have a factor which is L. Okay, so L has components. So it's sine theta cos phi, sine theta sine phi, and cos theta. Okay, and so if we look at the x and y components, we see that they have period 2 pi, not pi. Okay. So at least in this, I mean, but for a phase function which is symmetric in phi, the integrand here in this example has period 2 pi, not pi. But I think that this is still true, because if I were to make plot this this function f as a function of phi, so we could have say something like this. Let me try it. Put this here 2 pi, and then here I have 4 pi. Okay, so as long as this is periodic, I can always what I mean to say is that this integral, well, in this case is 0, but it's the same as starting from midway to. That's what I mean to say, is that because it's periodic, I can also perform the same integral shifted. And I think it should be very easy to prove. I think basically that that what I'm trying to say is that this is the same as the integral of epsilon whatever 2 pi plus epsilon times d phi f of phi is what I'm trying to say. And I think this is true, but I'm not all of a sudden I can't prove it. I mean, it's true for any trigonometric function, right? Like you have an example here. So why it should be very easy to prove that these two are equal. Okay, well, pending this small proof, I mean, we can still, one thing we can do, just not to leave this in the air, is I say, okay, suppose that we are in this situation where phi is symmetric, so the phase function is symmetric in this angle phi. Then in this case, we have this integral, like the integral in d phi from sine phi times a constant, okay, and from pi to 3 pi, okay, and this would be then well the primitive of this is cos phi evaluated between pi and 3 pi, and that's 0. That was easy. And the same for cos phi, okay? And it's also true that because it's 0, it's the same as the integral from 0 to 2 pi, okay? So in this case, where we have symmetry between in this angle phi, then this integral is equal to 0 to 2 pi, and it's also equal to 0. So in the end, well, it's good news. This term is indeed 0. If you can come up with a more elegant way to show this, please let me know. But I think we've invested enough time on this one. I think we need to move on. The bottom line we've realized here is that we were then doing this trick. We were evaluating the integral over all directions times the direction of equation 49. This is equation 49. So it's here, sorry. It's really the transfer equation. So the first term we rewrote in terms of our divergence. This one is going to be 0. This other one is going to give us the flux, and this last term is also 0 only if the phase function is forward backward symmetric. Okay. So grouping terms, we have the divergence is can be written as in terms of the radiation pressure tensor, which is the last equation here. So you have to read this as 3 equations. So the pressure tensor is the integral of k times another the k, which is, I mean, think of it as a matrix, right? Pij is ki kj times I. And so we have that this is the pressure tensor here, and we put it in compact form like this. Okay, so this works as long as we have forward backward scattering symmetry. This is more general than the previous derivation because what Rybicki and Langman use is this radiated transfer equation, where we could factorize the scattering contribution because we were assuming isotropic scattering. So this is the Rosseland approximation for isotropic scattering. Okay, now we're a bit more general here in restricting to forwards backwards scattering symmetry, which is true for atomic and molecular processes always. Okay, so for dust grains, it might not be true, but at least it's an approximation for dust grains. We then apply the local thermodynamic equilibrium and evaluate the pressure tensor, assuming that I is the Planck function. Okay, so the pressure tensor is I'm just applying this formula here. Maybe I should write it. Let me write it here so this is clearer. So what I'm saying is that the pressure is the integral over the omega of k pi times kj times I nu. And there's a factor of c here. Okay. And so this is what we're doing. This is the same. So the factor C is here. I've replaced I with the Planck function. Okay. And so if you evaluate this, it turns out that this is a pressure tensor is given by the Planck functions, and we have a diagonal matrix. Okay. So that when I is different from J, then this is 0. Okay. And so we replace this into equation 51, which is this compact form for the Rosseland approximation. And we end up with this expression for the flux in the direction Z. Okay, so you could replace this for the direction Y, the direction A, etc. So we find in the end the same result as in the previous derivation. Okay, so that was the previous the derivation from Rybicki and Lightman, where we assume plane parallel geometry and we assume isotropic scattering. But here we get the same expression, except that we do not need the plane parallel approximation, and we only require forward-backward scattering symmetry. Okay, so I'm sorry it took me so long. I got stuck here in this expression. Still not completely clear about this term here. I mean, it seems to be 0. Okay, but in reviewing carefully why this is 0, we realize that this derivation is restricted to forward-backward scattering of symmetry, which is something I had overlooked. Okay, so I think sometimes it's healthy to look at derivations in details and pick up an incompleteness here in my lecture. Okay, so you can now see that this this is true. Okay, so we have finally that this is interesting because we have that the radiation flux. Okay, so F in any direction. Okay, so dot S. Okay, is minus 4 pi times 3 alpha times dB nu over ds. Okay, so that's quite interesting because it gives us an idea of what the radiation flux is only based on local conditions. Okay, so we don't need to integrate the whole radiative transfer equation to have this answer in the limit of an optically thick medium. Okay. Now, this we can take this a bit further, and we can integrate over frequency, and we get the bolometric radiative flux. So we integrate over all frequencies, and we get then not the flux density, but rather the flux, the bolometric flux. Okay. We apply here that this is an application of the chain rule, the differentiation. Well, we have, let me, this is not completely clear. I think it's worth writing it down. So we have that the integral of d nu f nu of z is then the integral of d nu of minus 4 pi times 3 times dp nu over dz. Okay, but this depends on z only through the temperature. Okay, so this one is dB to dt times dt to dz. Okay, so that's what we did here. And the temperature doesn't depend on frequency, so this goes out of the integral. Okay. And here there's an interesting quantity. There's this integral over all frequency of the derivative of the Planck function compared to the temperature, corrected by this absorption coefficient. This quantity seems to play an important role. It depends on the microscopic properties through the absorption coefficient. Okay. This then is what governs the transport of bolometric flux, because if you pay attention, the factor here does not depend on microscopic quantities. It's only the local temperature and the linear position, I mean the coordinate, okay? This, on the other hand, depends on the microscopical processes through the absorption coefficient, okay? So we replace all of this with this definition. We define the Rosselin mean absorption coefficient, and this is a rather complex definition of it. So this is a definition. When we use this in what follows to replace this all this expression that includes the microscopic processes. Okay. With this, we have that. Well, here I've replaced the derivative over z to that of the derivative of any direction. Okay. This integral here in the denominator, the integral of the d nu of dB nu and dt. So yeah, it can be shown that this is 4 pi sigma t cubed. Okay, and so I introduced the Rosselin approximation, replace the normalization of the Rosselin coefficient here with this. This is the normalization of it, and it comes here into the integral. So that is yeah. So do you have questions so far? Because I think this is rather straightforward. It's not easy, but it's rather straightforward. So we see that well, I've got a typo here. This is not F nu. Let me correct it now, because then I'll forget afterwards. Okay, this is what I meant. So the flux, not the flux density, is given by this expression, it's compact form. Okay. So again, I've got news here. Sorry, I better correct for them immediately. Okay, so so that's interesting. Look, I mean, this is the equation we obtain. Okay, so the radiative flux is given by this compact form, but we can put it in an even more interesting expression by noting that we can take like you know that this is t cubed times dt. This is the same as dt to the fourth power. Okay, so that's important to note because it means that we can replace this temperature to the fourth power in terms of the energy density. So the energy density of a black body is proportional to the temperature to the fourth power. Okay, and so we see finally that the flux of radiation in the Rosselin approximation is proportional to the derivative of the energy density. Okay. So that is very similar to a diffusion process. So this is called also radiation diffusion, okay? Because when you have a diffusion process, you write that the flux of that quantity which is being diffused is proportional to the gradient of the quantity being diffused, as I've written here in equation 59. And we have a diffusion coefficient here, which is called D normally. Okay. Normally this diffusion coefficient then is written as 1/3 times the velocity of the particle which is carrying the transport, the particle responsible for the transport. So this is photons, so they go to the speed of light. Okay, and it's 1/3 for one of the each of the directions X, Y, Z. and L is the mean free path. Okay, and so this L here, if you replace into the expression above, the mean free path is approximately the reciprocal of the Rosson mean absorption coefficient. Okay, so this is the summary of the Rosson approximation. It's a very important approximation, very often in use, and we have that in the conclusion that the Rosson approximation is a diffusion approximation for the energy density of radiation. So we have that so you have the energy density of radiation depends on position through the temperature. Okay, so inside a star, so I think move this. Okay, so here in this logo I have on my presentation, you have a hot inner region, and you have that photon scatter all the way out to the surface. Okay, so instead of doing all the details of this random walk, we use Rosson approximation, where the energy density is being transported outwards by photons. And the energy density is that of the radiation mostly, and it's proportional, and it's given then by the temperature, by the local temperature. So we are in local thermodynamic equilibrium. The temperature can change. It's not, and can change with position. It's steady state. It doesn't change in time, but it can change as a function of position. And the gradient of the energy density is what leads to the flux. Okay, or the other way around. The flux is what leads to the gradient. Okay, but they're equal, and this is a very important way to remember the Rosson approximation. Okay, so this is very often in use in astrophysics in general. But the problem with the Rosson approximation, of course, is that we would like to be able to use it all the time, right? But there's a big problem with it, is that it's only really applicable to very optically fixed situations, because let me try and explain this. Okay. So let me write the Rosson approximation here. Okay, so we have the radiation flux then is approximately 4c divided by 3 alpha times du ds. Okay, and alpha is the alpha Rosseland, where the definition of the Rosseland absorption coefficient is this one. So this is the integral over all frequency of 1 over alpha times dpu. Okay. And divided by the normalization, which is 4 pi sigma t cubed. Okay. So do you remember what the connection is between alpha? So alpha is this absorption coefficient. Okay, this one here is alpha nu. So alpha nu, how do we write it in terms of microscopic quantities? You remember, it's the density of absorber times the cross section of the absorbers. Yeah. Okay. So we can also write this as the mass density times kappa. Okay, good. So what happens if we have so what happens if the density goes to 0? If the density goes to 0, then we have well, this is the reciprocal of 1 over half fire. Sorry. This is the definition of the reciprocal, okay? So if the density goes to 0, alpha R goes to 0, and this flux goes to infinity. Oops. So when we have a medium where the density goes to 0, we have an infinity for the radiation flux. That's not good. I mean, it's in the end, Rossman's approximation can only be applied deep into the star. It cannot. When you get close to the photosphere or the star, then we can't use it anymore because we reach this problem that the absorption, the Rossmann mean goes to 0. Okay. So in order to extend Rossmann's approximation a bit further into the optically thin regime, okay, when the optical depth is order 1, people use the lambda controlled diffusion. And this is completely put by hand. There's no rigorous derivation of this. It is the result of empirical fits to sophisticated hydrodynamical simulations, including radiative transfer, which suggest that we can extend the Rossmann approximation a little bit further into the optically thin regime using the lambda controlled diffusion, which is basically this. We have we use the same expression as the radiation as a Rossmann approximation, but we correct it for a factor of lambda, which is a complicated function of, in the end, the gradient of the energy density and the normalized by the energy density itself. Okay, so I mean, in the end, it turns out that this lambda in the limit of very small alpha r is also proportional to alpha r. So that corrects for the singularity and the low density limits. It corrects the alpha r on top and in the bottom, and it doesn't diverge in the limit of low density. So there's an example in my paper here in 2019, but I only mentioned this so that you're aware that there are extensions to the Rossmann approximation, which can help in some cases. Okay, so this goes beyond the contents of this lecture on radiative processes. But okay, I think this is it for the Rossmann approximation. And
Professor,
yeah.
sorry to interject. I think the previous slide, again, this that F nu will be F, I guess.
Oh, thanks. Yes, thank you very much, Patricia. I'll correct for this right away. Good. Okay, so now I mean, we are running out of time again. What time is it? Because I think that the clock on my computer is a bit upset. Yeah, we only have 4 minutes left. So in what remains of this chapter, I need to talk to you about the Eddington approximation, and that's also quite important to know. It's also covered in the textbook, in how we can use it to solve the radiative transfer equation. So this looks complicated. It is a little bit difficult to follow, but it's straightforward. And unfortunately, we didn't have time to do it today, so we'll have to go into it next Tuesday. So we need to agree on a time for the exam. We have to do the first exam. Okay, so I think Nikya, you couldn't attend the lecture last time, but just to briefly put you up to date, the idea is for you to hand in the first homework, which is simply doing all the problems in chapter 1 in IBK Enlightenment, hand them in by next Tuesday. Okay. So next Tuesday we'll finish on the Eddington approximation. I think that if you do the homework by next Tuesday, this should be a lot easier, and this should be a good opportunity to ask me questions. Okay. Then hopefully we'll finish this on Tuesday, and then I suggest that we start the exam week on next Thursday. Is that okay for all? I mean, because I know that especially in India, you are coming back from a very significant ordeal with COVID. So are you in good shape to, or at least are you how can I say this? In sufficiently good conditions to take an exam? That's my question.
I think it's okay with me. Thursday, yeah, it's fine. I think. So how the test will be conducted? Like that I'm not sure. So it will be online. Or...
No. I've tried to explain this. The exam is like the homework. I'll give you a homework. You have a whole week to do it. The exam normally, if we weren't in COVID situation, you will take an exam in a classroom at Sarakalan. Okay. So the exam is designed to be done in 3 hours. Okay. It should be doable in 3 hours. But given the circumstances, I'm just going to give you the exam, and you'll have a week to do it. And you can use the whole internet. You can access the internet, look at the textbook, look at your notes, run computer programs, do whatever you like, you know. But the only thing you cannot do is discuss the exam with someone else. Okay.
Okay.
Now, along with the exam, I'll be giving you references where the exam is solved. Okay. So you should, I mean, but that doesn't mean it's easy, because the references are not easy. but it's a good way to to really consolidate what we are learning here, because it's I mean, you know, when you go into postgraduate studies, there's so many things to study. You know, you do cosmology, you can do galaxies, you can do so many different things. You know, you cannot learn everything, but there are some tools which are crucial anywhere, and one of them is radiative transfer. Okay, so this is like important to really consolidate in your memory about all these tricks about the Rosseland approximation and the Eddington approximation. So then afterwards, when someone tells you, yeah, of course we use the random walk or we use the Eddington approximation, you know what it is. You know, maybe you don't remember exactly what it is, but if we have an exam, then it'll stay in your memory later on. Okay. Now, if you are in good shape enough, then we'll start the exam next Thursday. That will be the exam week. And then you'll have to hand in your exam the following Thursday, okay? We won't be doing any lectures in between. You'll have the whole week devoted to this, okay? And that's why I need you to finish the homeworks before we start the exam, okay?
Professor, here I want to say something.
Yeah, go ahead.
Actually, Professor, next week I'm also having some like deadline for other courses assignment. So like I'm worrying like how will I do this?
Oh, you say you have another deadline next Thursday for another course?
Yeah, for planetary science, I have to like submit assignment for.
Mm-hmm. But when is your deadline? When do you have to hand them in?
Yes, like for me it is for until the Saturday. actually the last week I had some problem, and like in this week as well. So like professor have extended my deadline until the Saturday. So like
This Saturday or the next one?
next one actually.
Okay. Well, in this case, well, I need you to, I need all you, I mean, once all of you have handed in your homeworks, we'll convene again and see if we are in a good situation to take the exam, okay?
Okay.
But the first step is then to hand in your homeworks, okay?
Yeah. Okay. Yeah.
And then the homeworks you can discuss. The homeworks is okay to discuss, to ask about about the problems with Rafael, or among yourselves. It's absolutely fine to discuss the homework, okay? But you have to at least write down each problem on your own, okay? So you know how to solve them. If
Yeah.
you've done that, then doing the exam should be easy, okay?
Yeah.
But in any case, I don't want to stress anybody. If you have if you don't do well in the exam, you're completely lost and you don't find a solution, and your final grade is less than a 5 out of 7, then I'll replace the grade with a presentation or whatever. But the idea is that everyone will have a good grade, okay?
Okay.
Okay, there's no way to fail here. But just so that just to ease the pressure, okay? Hopefully everyone nobody will need it, but in case you do, then we change the exam by a presentation, okay?
So what we will do, like we will discuss all the things between us, and we will confirm you by the next Tuesday. Is that fine for you?
Well, right now, what I need you to do is to hand in first homework, which is all the problems of the chapter 1, as soon as possible. Hopefully next Tuesday, if you count next Thursday, and if you count then the following Tuesday. I understand the situation, and it's not going to be dramatic if you do not. But I think we're running late, and it's important to gear up at the moment. Okay. I mean, there's a lot of topics to do. This chapter is the most important one, but hopefully we can look at as much material as possible. But I'm reluctant to proceed with the rest of the lecture if we don't wrap up this part first.
Okay.
Okay. So so this is it basically. My message is: hand in your homeworks as soon as possible, hopefully next Tuesday, and then if not, then next Thursday. If not, well, then the subsequent Tuesday. It's okay, but once you've done that, then we can arrange for this exam. And please don't be scared about the exam, because as I explained, we will replace the exam by a presentation if you don't do it.
Okay. Yeah, thank you very much, Professor.
Okay, you're welcome, Nietzsche. Then in this case, we'll finish here. Sorry to have extended a little bit more. So see you next Tuesday. Ciao.